everyone, welcome back to my YouTube channel. In this video, I'll be taking a look at the golden ratio, taking a look at phi. And I know that I've made a video about it in the past, but in that video about a year ago, I'm only talking about the properties of phi and its connections to various mathematical, scientific, and astronomical sites. So, let's start by talking about the golden ratio in a more mathematical perspective in this video. So the golden ratio is often denoted with the Greek letter phi. This is the lowercase letter. There's also another capital letter, but this is the more famous one. So let's take a look at the golden ratio. So firstly, let's talk by what is the definition of the golden ratio. Well, there are two definitions and maybe several more, but I'm going to take a look at the two most famous ones. The first one, let's take a segment length, like this, and the length of it all is C. And then let's divide it into two places, into A, the bigger one, and B, the smaller one. And then we have to subdivide it in a certain way such that the ratio between the two sides, A over B, is equal to the total side, C, or we can write as A plus B, divided by the larger one, A. So this is in and of itself a very interesting ratio. So let's use this equation to try and figure out what the golden ratio, what phi really is. So I'm going to divide, I'm going to erase this a little bit more. So let's take a look at this ratio. Firstly, let's say that phi is going to be A over B, and that is what we're searching for. So let's divide this fraction, A plus B over A, that can be expressed as A over A plus by B over A. And then A over A is equal to 1, because any number divided by itself is equal to 1. So then that means that A over B is equal to 1 plus by B over A. 1 plus by B over A. And now let's take a look. A over B is equal to phi. So you can write this as phi is equal to 1 plus by B over A. Well, B over A is the reciprocal of A over B. Reciprocal means we switch the numerator and the denominator. So, we have to take the reciprocal of phi then, because A over B is equal to phi. And because phi is equal to phi over 1, the reciprocal, phi over 1, sorry, the reciprocal of it is going to be 1 over phi. We switch the numerator and the denominator. So then, phi is equal to 1 plus by 1 over phi. And then we can solve it. It's just a simple algebraic operation with one variable. So let's multiply everything by phi, because I don't want to have the variable in the denominator. So we have phi times phi, that is phi squared, is equal to 1 times phi, that's phi, plus by 1 over phi times phi, that is 1. And then we can isolate all of the variables and constants at the left side. So we get phi squared minus by phi minus, no, not theta, minus by phi, sorry, minus by 1 is equal to 0. And now we can factor it out or use the quadratic equation or complete the squares. But I'm only going to use completing the squares method at this time, because I think that it's a much better method to calculate it. So then let's divide this into, this is the first value and this is the second value. So we have phi squared minus phi, and then we have negative 1, and here equals 0. I'm giving some space between these. Oh, this is supposed to be phi. I'm giving some space between these so that we can use some algebraic operations. So let's take a look at this value over here, phi. What is the coefficient of the variable? That is 1. Negative 1, sorry, because there's a negative in front of it. And then what completing the square do is we're going to divide by 2, then we're going to square it. The negative cancels out, we get positive 1/4. So we're going to plus this value by 1/4. And we've completed the square. However, we can't just willy-nilly add a value to equation. That's going to erase the whole equality. So we have to minus it by 1/4 again. So what this has done is, we're not changing the value for the equation. We're adding a value and then minusing it. It's still equal to itself. However, we've done it in such a way that we can factor this into a perfect square. So let's do that real quick. So what is the factorization for phi squared minus by phi plus 1/4? Well, that's going to be phi minus by half squared. Don't forget the minus 1 minus 1/4. That's going to be what? Minus 5/4. Yep, it's going to be equal to 0. So then we can add 5/4 to both sides to isolate this expression. This comes up, so we're going to get that phi minus by half squared is equal to positive 5/4. So now we can square root both sides to erase the exponent in here. We square root this and we square root this. So then we're going to get that phi minus half, because the square root cancels out the square. So you get that phi minus half is equal to square root of 5/4, which is basically square root of 5/2. I'm going to drag the equation up here. So then, phi minus half is equal to square root of 5/2. Let's plus both sides by half. So what do we get? Well, we get 5 because the negative half and positive half cancels out. So you get that phi is equal to square root of 5/2 plus half. Square root of 5/2 plus half, which is basically just equal to 1 plus square root of 5/2. And there you go. That is the expression for phi, the golden ratio. So if we evaluate the values in a calculator or counting it ourselves, we can figure out that phi is going to be a number approximately 1.618 and so on. So that's the first way we can take a look at phi, which is a segment length, and then we divide into two places, a and b, such that the ratios are like this, and then we can use computing the squares and polynomials to get the value for phi is 1 plus square root of 5/2 or 1.618. So that's the first way we can take a look at phi, which is having a segment length divided it by 2 in such a way that there's the ratio which is equal to phi. However, let me introduce you to another topic. So firstly, let's take a look at a continued fraction. A continued fraction. So firstly, let's think what is a fraction, essentially. So fraction is going to be when we have an integer, a whole number, a, and then we divide it by another integer, b. This is basically the essence, the heart of a fraction. And then there are many different types of fraction. There is a mixed fraction, a negative fraction, but we're just going to take a look at fraction in general. And basically, a fraction can express all rational numbers. In fact, they're called rational numbers because they can be expressed as a fraction. For example, 5. That's a rational fraction. That's a rational number, sorry. Because this can be expressed by a ratio of two numbers, which is a over b, in which a is 5 and b is 1. And this is true. 5 is 5/1. And let's take a look at another rational number. 3.4. We know that 3.4 is also a rational number because it can be expressed in a fraction, which is 34/10. And even an infinitely recurring decimal, such as 0.33 and so on, denoted by this line over here, is also a rational number because it can be expressed as 1/3. Just try to evaluate. This is the correct value. And actually, there are much more numbers that are not rational, irrational numbers, that cannot be expressed by a number a divided by another number b. And there are a lot of different irrational numbers. Let's take a look at the most famous ones. Pi, e, square root of 2, and much more. All of these cannot be expressed as an integer divided by another integer, which is what they call an irrational number. And then, let's take a look at the most famous irrational number, pi. So we know that many have written pi as an irrational number, 22/7, but this is just an approximation. So what if we take that approximation to another level and try to use a certain value of a fraction to approximate pi very good? So let's think about it like this. So let's take a look at a continued fraction. So a continued fraction will take a form of a plus 1 over b plus 1 over c plus 1 over d, and so on. And this is actually a method of calculating and expressing rational numbers, because we can express it as an infinite fraction. So let's take a look at pi. We know that pi is approximately 3.14159 and so on. I've actually remembered quite some decimals for pi. So let's try to put pi in this form. So firstly, we know that a is going to be 3, because that's going to be a number on top of here. So pi is going to be 3. But we know it's going to be 3 plus a bit, right? Which is 0.14159. So I'm going to take my calculator in here, and I've already put some values on the screen in here. So if we take 0.14159, which is basically just pi divided minus by 3, and then we can write it as an inverse of it. What is 1 over that value? That's going to be approximately 7. So it's 1 over 7 plus a bit. And what is that a bit? Well, we can just minus the value by 7, and it will be approximately 0.06, which we can also express as a fraction. We can write it as 1 over, we can take 1 divided by that value, there will be 1 over 15 plus a bit. So you can say 15 plus a bit. And this a bit value, we can multiply by 15, and the value is about 0.996. And if we take the inverse of it, we get it's going to be about 1 over 1. So we can say it's about 1 over 1. But it's also plus by a bit. I'm going to speed up the process. It's going to be 1 plus 1 over 292 plus 1 over and so on. So actually, this method of expressing pi using conjugate fraction, like what we've done before, is actually a very good approximation for pi. And it doesn't take that much work. Even this value can already express pi up to, what, 10 decimals? I haven't really checked it, but it's a very good approximation. So let's analyze this a bit. If we take a look at this fraction, we can see that 3 plus 1 over 7, only this value, is equal to 10 over 7. The value we've looked at every day. But what if we add 1 over 15, this value? Then it will add more depth upon the approximation for pi. And what is the most efficient way to approximate it? Well, let's take a look at this number, 1 over 292. This number is a very small number because the numerator of it is very big, and we know that for a fact. So, all of these values are going to approximate pi step by step, because once we add 1 over 7, it adds pi more digits. After we add 1 over 15, it's adding pi more digits. But when we add 1 over 292, that doesn't really change much of pi, right? Because it's only adding a very small number. So that means that all of the value in here are already very good approximations for pi. Because even if we add this more fraction, it will only change a very little bit. So it doesn't change that much for pi. And this is the definition of an irrational number that is not very irrational, because it can be well approximated by just several fractions like these. And that's actually saying that pi is not very irrational. So that begs another question. Is there the most irrational number? So let's say that our hypothetical most irrational number is x, our beloved variable. So if we want to express x as the most irrational number, then we have to make sure we don't make the same mistake as pi. Pi makes a mistake that there is one value in his continued fraction, which is 1 over 292. And this is such a small decimal that all the previous values for pi are already very good approximations of it. So we should make that all of the fractions within the continued fraction very big fractions. And we can do it by making the denominator as 1. Because 1 divided by 1 is 1. Quite a big number, right? And we also can do things like making the denominator as decimals, like 0.5, which will make it 2, because that's the rule for continued fraction. Everything has to be an integer. So we can say that our continued fraction must use the number 1 for everything, so that it is very hard to be approximated by just small fractions. So then we can already conclude that our hypothetical most irrational number is going to be 1 plus 1 over 1 plus 1 over 1 and so on. Because if we use 1 as the values throughout this, then it's going to be very hard to be approximated, which makes it very irrational. So then let's just take a look at this continued fraction and quite simplify. So let's make this equal to x. Now let's take a look at it. If this is equal to x, which is 1 plus 1 over and so on, well, if you look at this value over here, this is also equal to x because it's 1 plus 1 over 1 plus 1 over 1 and so on. So we can write this as 1 plus 1 over x is equal to x. And there we go. That's the equation that we've tackled before, the one with phi at the first part of the video, in which x squared minus x minus 1 is equal to 0. You can try to solve it again using quadratic values and more, but this is basically the value for phi. And we've already managed to express phi twice. So basically, we've already managed to express phi as the ratios within segment lengths and then try to do the algebra for it. And we've also expressed it as the most irrational number. So what does that mean? So that means that the most irrational number, it's very hard to be approximated by just small decimals, unlike pi. And I will be talking more about this notion of irrationality in the future videos. I will be talking about Fibonacci numbers, Lucas sequence, and much more, but there will be a story for next time. So if you like this video, don't forget to subscribe to my channel so you'll be notified whenever cool videos like this show up, and don't forget to like the video and share this link to your friends. Thank you for watching.